Somewhere in the disk of the Milky Way, in a region of space where no light reaches the human eye without the aid of instruments tuned to frequencies far beyond the visible, there is an object roughly 20 kilometers across. Not 20 kilometers wide the way a city is wide, spread out, with edges that fade into suburbs and open land, but 20 kilometers in every direction, a near perfect sphere, compact and absolute. It turns slowly in the dark. It does not orbit anything. It has no companion, no nearby warmth, no star to circle. It simply exists there, dense and hot and solitary, as it has existed for several thousand years, since the night the star that made it tore itself apart. 20 kilometers is not, by most measures, a large thing. A person could drive across 20 kilometers in roughly a quarter of an hour on an open road. A city like Chicago, or London, or Sydney spreads its center across distances like that and calls it ordinary. Place this object at the heart of any of those cities, and its edge would not reach the outermost neighborhoods. You could look at a map of the city and point to where the object began and where it ended, and the gap between those 2 points would seem like almost nothing. And yet inside that sphere, compressed into that unremarkable diameter, sits more mass than the entire sun contains. The number attached to this compression is large enough to stop the mind before it starts. A single small spoonful of the material at this object's surface, a volume that would fit easily inside a thimble, would, if somehow placed on Earth, weigh approximately 1 billion metric tons. Not 1 billion as an approximation, as a rough gesture toward a large quantity, but 1 billion as the honest figure that arises from the density of nuclear matter pressed together so tightly that protons and electrons no longer exist as separate things. At densities like these, those particles are forced into each other, merging into neutrons that pack together in a state the universe rarely permits, and that nothing made by human hands has ever approached. The object in that dark corner of the galaxy is made almost entirely of those neutrons. It is, in the plainest language, a neutron star. And neutron stars, even taken on their own terms, are already among the most extreme things in the observable universe. An object the mass of the sun, pressed into a sphere the width of a city, a surface temperature of millions of degrees, a gravitational field so intense that the escape velocity at the surface reaches roughly half the speed of light. These are the ordinary properties of ordinary neutron stars, the quieter members of the family, the ones that pulse steadily like cosmic lighthouses or drift in silence through the void. They are extraordinary in the way the deepest ocean trench is extraordinary, beyond direct human experience, almost beyond conception, and yet catalogued, measured, and in a rough sense understood. The object turning slowly in that dark region of the galaxy is not one of those. It belongs to a rarer category, a subset so much more extreme that placing it beside an ordinary neutron star feels like placing the surface of the sun beside a warm afternoon. Its magnetic field is not merely strong. It is strong at a scale that rewrites what the word can mean, strong at a scale where the field itself begins to alter the fundamental geometry of matter. This object is a magnetar, and there are, across the entire span of the Milky Way and the smaller galaxies gathered around it, only around 30 of them known. To begin to understand the magnetic field of a magnetar, it helps to begin somewhere familiar. A refrigerator magnet, the kind used to hold a note or a photograph to a metal surface, generates a magnetic field of roughly 100 Gauss. That is enough to hold a few sheets of paper. A hospital MRI machine, which is a precisely engineered instrument designed to generate the strongest safe magnetic field that can be placed around a human body, reaches somewhere between 10,000 and perhaps 60 or 70,000 Gauss, depending on the system. At those field strengths, the machine has to be carefully managed. Loose metal objects become dangerous. Certain medical devices cannot be brought near it. The fringe field alone requires exclusion zones. These are among the strongest sustained magnetic fields that exist in ordinary human environments. The surface of a magnetar begins at around 10 trillion Gauss, 10 to the 13th power, and in the most intense examples reaches 1,000 trillion Gauss, which is 10 to the 15th power. Each step upward in that sequence is not an increment, but a transformation. The gap between the MRI machine and the lower end of the magnetar range spans roughly 9 orders of magnitude, which is to say, the factor of increase is comparable to the difference between 1 meter and the distance from the Earth to the Sun. And even within the range of magnetar fields themselves, from the weaker examples to the strongest, there is another 2 orders of magnitude of variation, a 100-fold spread that would itself dwarf anything found on Earth. At a specific threshold, approximately 44 trillion Gauss, a value called the quantum critical field strength, something happens that has no equivalent in ordinary physics. The magnetic field becomes strong enough that it begins to distort the shape of the vacuum itself, pulling virtual particle pairs into brief asymmetric configurations that would not arise in a weaker field. And for matter that exists in the presence of such a field, the consequences are structural. A hydrogen atom, under ordinary conditions, is very nearly a perfect sphere. The electron orbits the nucleus in a cloud that is on average roughly spherical, with no strong preference for any particular direction. In a field above the quantum critical threshold, that changes. The electron's orbit is constrained by the field into a direction along the field lines, and the atom is drawn out into an elongated shape, a cylinder rather than a sphere, roughly 200 times longer along the field direction than it is wide. The geometry of the simplest atom in the universe is reshaped by force alone. This is not a small perturbation. This is not a gentle distortion that leaves the atom recognizable in a slightly altered form. The hydrogen atom at the surface of a strong magnetar is a fundamentally different object from the hydrogen atom in the air of a room or in the atmosphere of the sun. Its chemistry is different. Its interactions with light are different. In a meaningful sense, the matter at a magnetar's surface is matter in a state that does not exist anywhere else in the universe that has yet been found, shaped by a force that operates at a scale nothing else in nature reaches. The idea that objects like this could exist was not always obvious. For most of the history of neutron star research, after the theoretical prediction of neutron stars in the 1930s, and the first observational confirmation through pulsars in the 1960s, the focus was on the rotating kind, the objects that beam radio waves from their magnetic poles with such regularity that the first ones discovered were briefly, half seriously considered as possible signals from an extraterrestrial civilization. Those pulsars are powered by their rotation. As they spin, they lose energy to the radio and other electromagnetic radiation they emit, and they slow, predictably and measurably, over time. The physics is elegant and consistent. The slowing is clock-like. The field strengths of ordinary pulsars are large, billions and perhaps trillions of Gauss, but they sit below the threshold where quantum effects on matter become relevant, and their behavior, while extreme, follows from principles that were well understood within a few decades of their discovery. A different class of objects had been observed from the 1970s onward, sources that emitted soft gamma rays and X-rays in irregular volatile bursts, with no clear radio pulse and no obvious power source of the kind that explained pulsars. They were eventually cataloged under the names soft gamma repeaters and anomalous X-ray pulsars, two classes whose names reflect the confusion of their early study. They repeated, which was unusual for gamma ray events, and their X-ray emission was anomalous because it was far brighter than any pulsar powered by rotation could sustain. Their rotation periods, when measured, were slow, not milliseconds, as fast pulsars spin, and not the fraction of a second typical of young pulsars, but 1 second, 2 seconds, sometimes as many as 12, and they were slowing faster than ordinary pulsars slow, which implied either an unusual braking mechanism or an unusually strong magnetic field doing the braking. In 1992, two astrophysicists, Robert Duncan and Christopher Thompson, published a theoretical framework that brought these observations into a coherent picture. Their model proposed that a specific class of neutron star, born in specific conditions during the collapse of a very massive star, could develop a magnetic field not through the gradual accumulation of a progenitor star's field as it compressed during collapse, but through a fundamentally different process, a brief, powerful dynamo operating in the first seconds of the neutron star's existence. If the proto-neutron star, the hot, dense, newly formed object that exists in the first moments after core collapse, was spinning fast enough, and the interior was hot enough and turbulent enough, convective currents rising and falling through nuclear density material could interact with the rotation to amplify a seed magnetic field by many orders of magnitude in a window of only a few tens of seconds. The result would be an object with a surface field of 10 to the 14th or 15 Gauss, the object Duncan and Thomson called a magnetar. The name has stayed because the thing it names is real. In the years since, the observational record has accumulated enough evidence to confirm that the soft gamma repeaters and the anomalous X-ray pulsars are both populations of magnetars, and that they share the fundamental signature Duncan and Thomson predicted: magnetic fields far above the ordinary range, volatility driven not by rotation, but by magnetic instability, and slow rotation periods that reflect both the initial spin down during the turbulent birth phase and the subsequent relatively rapid loss of rotational energy in a strong field environment. They are not powered by their spin. They are powered, in a real sense, by their own field, by the energy stored in the extreme magnetic configuration generated during the first seconds of their existence, slowly released over the following 10,000 years or so as that field evolves, shifts, and dissipates. 10,000 years is the relevant timescale. After roughly that long, theoretical models suggest the process of magnetic field decay has reduced a magnetar's field strength enough that its behavior begins to resemble an ordinary neutron star, less volatile, less luminous in X-rays, no longer producing the intense bursts that define the active phase. The magnetar, in a sense, quiets down. It does not disappear. It does not explode. It simply fades into the background population of neutron stars, its exceptional past invisible in its present state, carrying nothing externally to mark what it once was. If this picture is correct, it means that for every magnetar currently visible in the sky, there are vastly more former magnetars, neutron stars that went through the active phase and then settled, scattered through the galaxy in numbers that dwarf the 30 or so objects currently known. 30. It is a number small enough to hold as a picture. If each known or suspected magnetar were a grain of coarse sand, the entire census could be gathered into a cupped palm, With room left over, 30 objects spread across a galaxy that contains somewhere between 100 and 400 billion stars. 30 objects in a structure so vast that light, traveling at roughly 300,000 kilometers per second, takes 100,000 years to cross from one end to the other. In a census of the galaxy's total population of neutron stars, estimated in the hundreds of millions, based on the rate of supernova events over the galaxy's lifetime, these 30 are the extraordinary few that formed under exactly the right conditions in that narrow window, with a progenitor massive enough, and a spin fast enough, and a convective interior turbulent enough for the dynamo to run at full power for its brief window before cooling silenced it. The 30 are concentrated mostly toward the inner part of the galaxy, toward the denser regions where massive stars have formed and died in greater numbers over the galaxy's history. They sit along the plane of the Milky Way, scattered through the spiral arms and their edges, each one a faint source of X-rays in a crowded region of space where much else is also emitting at those frequencies. Finding them required the development of space-based X-ray telescopes sensitive enough to detect their glow at distances of thousands of light years, and distinguishing them from other X-ray sources required years of patient observation and the accumulation of timing data precise enough to measure their slow, erratic rotation. They are not easy objects to find. They do not announce themselves the way bright radio pulsars do. They glow in a wavelength the human eye cannot see, from a distance so great that their angular size is undetectable with any current instrument, and their defining property, the field strength, cannot be measured directly, only inferred from the rate at which they are slowing and from the characteristics of their emissions. The rotation periods of these objects, the time it takes a magnetar to complete one full turn, cluster between 1 second and about 12 seconds. For comparison, an ordinary young pulsar might spin dozens of times per second, and the fastest known pulsars, recycled through mass transfer from a companion star, spin hundreds of times per second. The magnetar's slow turning is partly a consequence of its active field. The extreme magnetic environment breaks the rotation efficiently, and the initial spin down during the hot early phase of the star's life was rapid. What is left after thousands of years is a slow, almost stately rotation, one turn every few seconds, in the dark, surrounded by a magnetosphere of intense and tangled field lines. In that magnetosphere, particles are accelerated to relativistic speeds and radiate broadly across a wide range of energies. The emission from an ordinary pulsar is dominated by the radio band, produced by a coherent process in the magnetosphere that generates the familiar lighthouse beam. The emission from a magnetar, even in quiescence between the bursts and flares that mark the active events, is dominated by X-rays, with luminosities that can reach 10,000 times the sun's total energy output in all wavelengths. A magnetar glows continuously with the energy of 10,000 suns from a surface spanning 20 kilometers. That glow comes not from nuclear burning, as a star's does, and not from rotational energy loss, as an ordinary pulsar's does, but from the slow, ongoing dissipation of magnetic energy through processes in the interior and at the surface. It is energy stored in the field itself, leaking steadily into the surrounding space as heat and radiation. The surface temperature of a magnetar reflects this excess heat. Ordinary neutron stars cool predictably over time, their residual heat from formation radiating away over thousands and millions of years. Magnetars are hotter than they should be, their surfaces running at several million Kelvin, even in objects old enough that simple cooling models would predict much lower temperatures. The extra heat is magnetic in origin, the result of processes deep inside the star that channel field energy into the crust as electrical currents and mechanical stress. The surface blazes in X rays, not because it is young or because something is burning inside it, but because the field is always slowly yielding its stored energy to the surrounding space. A surface temperature of several million Kelvin corresponds not to visible light, as a star's surface does, but to the X-ray band. If a human eye could somehow observe a magnetar from a safe distance, which cannot exist for reasons the physics makes clear, it would see no glow at all in the ordinary sense. The light coming from that surface is at frequencies far too high for the retina to register. To the instruments that actually observe these objects, satellite-based X-ray and gamma-ray detectors, carefully pointed in the direction of a known source, the magnetar appears as a steady, relatively faint point of emission in X-rays. Occasionally, in the active phase, brightening in sudden bursts that can for fractions of a second outshine the entire rest of the galaxy in high-energy light. But between those active events, the thing is simply there, turning slowly, glowing in X-rays, cooling imperceptibly toward a quieter future, decade by decade and century by century. The field that makes it what it is decays on timescales of thousands of years, and in that decay lies both the source of its activity and the clock that measures how long the active phase lasts. When the field has weakened enough, when the decay has run far enough that the magnetara can no longer sustain the intense emission, when the internal stresses have fallen below the threshold needed to drive the crustal activity that produces bursts, the magnetar becomes something else, something quieter and ordinary by the standards of neutron stars, which is still extraordinary by the standards of everything else. There is something settling in the image of an object that is, by cosmic standards, very small, carrying within its 20-kilometer interior a concentration of energy and field and density that has no parallel anywhere in the observable universe, not in the cores of ordinary stars, not at the center of the galaxy, not in the laboratory, not in any particle accelerator yet built or planned. The magnetar holds its condition not by any ongoing process of replenishment. It is not burning anything, not accreting anything, but simply by being what the dynamo made it in those first few seconds after the star that preceded it collapsed. Whatever field strength was achieved in that window is the field strength the magnetar carries forward. It is a record of a moment, sealed into the interior of a collapsed star, and carried through the following millennia as a slowly fading inheritance. The hydrogen atom stretched into a cylinder 200 times longer than it is wide, the surface glowing at millions of Kelvin in frequencies the eye cannot register. The rotation period measured in full seconds, slow and heavy in the magnetic void. The total luminosity reaching 10,000 times the sun's from a surface the size of a city. Each of these is not a description of an extreme version of something familiar. Each is a description of a regime where the familiar rules have been replaced by others, where quantum electrodynamics governs the structure of atoms, where the nuclear strong force determines the rigidity of the crust, where the magnetic field is not a background condition, but an active structural element of the matter itself. In the plane of the Milky Way, roughly 10 of these objects are confirmed. Add the candidates, sources whose behavior is consistent with magnetar identity, but whose field strengths have not been precisely constrained, and the number rises to around 30. 30 points of intense X-ray emission, scattered through a galaxy of hundreds of billions of stars, each one the remnant of a rare event that required a very massive progenitor star and a very specific set of conditions in the few seconds after its death. The rarity is not an artifact of incomplete surveys, though improved surveys will likely add more candidates. It reflects the genuine narrowness of the conditions required. The initial spin period must be short enough, the convective energy high enough, the cooling time long enough for the dynamo to operate, and still brief enough that the dynamo shuts down before the field is tangled into something weaker. Those conditions are met rarely, and the objects they produce last in their visible, active form for only a brief chapter of the galaxy's long history. The slow turning in the dark continues. The field threads outward into the magnetosphere in configurations too complex for any simple geometry to capture. The surface radiates its excess heat into the space around it, which is cold, the thermal background of intergalactic space, barely above absolute zero, and the contrast between the object's surface and its surroundings is perhaps as stark as any contrast in the physical world. Millions of degrees at the surface, a fraction of a degree above zero in the space surrounding it, separated by the sharp edge of an object 20 kilometers across. The field weakens, year by year, in amounts too small for any current instrument to detect directly. The rotation slows, second per period per year, accumulating into a measurable quantity over the span of observation campaigns that run for years or decades. And the object is not alone in this. There are others, the same object, in different stages, at different points in the galaxy, at different ages. Some are younger and perhaps more active. Some are older and perhaps already fading toward that threshold where the X-ray luminosity drops below detectability and the magnetar becomes simply another neutron star in the background. The ones known now are the ones that happen to form close enough and recently enough and actively enough that their emissions reached Earth's instruments during the decades in which human beings have been looking in the right frequencies. The ones not known vastly outnumber the ones that are. What is known, with the confidence that comes from decades of observation and from the consistency between the theoretical models and the measured properties of real objects, is that the magnetar is not an artifact of imagination or an extrapolation beyond reliable evidence. It is an object in the sky, 30 of them roughly, or perhaps a few more with continued observation, 30 extraordinary small dark things turning slowly in the plane of the galaxy, each one a record of a specific moment of catastrophic collapse, each one carrying in its interior a field no other object in the universe is known to match, each one fading slowly toward a quieter future, while still for now maintaining the condition that makes it what it is. The entire census of known and candidate magnetars, every confirmed source, every tentative identification, every object whose behavior has been interpreted as consistent with magnetar physics, could be represented as 30 faint, scattered points on a map of the galaxy. 30 points among the hundreds of billions of stars. 30 small, dense, hot, magnetically extreme objects, each one 20 kilometers across, and each one containing more mass than the sun. If those 30 points were grains of sand, they could be held in a single cupped hand. They could be counted on the fingers without needing to start over. That hand, with its 30 grains, would be holding the most magnetically extreme objects known in the observable universe. Objects where the field is strong enough to deform the vacuum, to reshape the simplest atom, to drive luminosities from a city-sized surface that exceed the sun's output by factors measured in thousands. Objects that exist for only 10,000 years in their active form, before the field that defines them weakens past the threshold and the magnetar becomes simply a neutron star, carrying no external mark of what it once was. Objects so rare that in a galaxy hundreds of thousands of light years across and billions of years old, Only 30 can currently be found. Small, dense, hot, slow, magnetically extreme, beyond anything else in the catalog of observed phenomena, scattered faintly across the inner disk of the Milky Way, each one turning once every few seconds in the cold dark between the stars, each one glowing in X-rays no eye can see, each one the product of a few extraordinary seconds in the life of a dying star. 30 points of light that are not really light in any ordinary sense, too energetic, too focused in frequency, too remote for the senses to reach. 30 objects quietly being what the physics of extreme field strength allows, in the patient dark of the galaxy, one slow rotation at a time. In the core of a star, 20 times heavier than the sun, iron had been building for thousands of years. Not the iron of slow geological patience, not the iron of cooling lava or ancient seabeds, but iron forged in the nuclear furnace of a stellar interior that burned at temperatures no planet had ever approached. Layer upon layer, the star had spent its life fusing lighter elements into heavier ones, working outward from hydrogen to helium, to carbon, to oxygen, to silicon, each stage burning hotter and faster than the one before, each producing a new shell around the growing iron core at the center. And iron is where the process stops. Iron takes in more energy than it gives back. It cannot be fused for a profit. So the iron simply accumulated, day after day and year after year, a growing ball of inert metal at the star's center, supported only by the outward pressure of electrons crowded so tightly together that quantum physics itself refused to let them compress further. That support is not infinite. There is a ceiling to what electron pressure can hold. When the iron core grew to roughly 1.5 times the mass of the sun, it passed that ceiling. The electrons were overwhelmed. They were forced into the protons around them, combining into neutrons and neutrinos in a reaction that drained the pressure, holding everything up. And then the core fell. It did not collapse slowly. It did not crumble or slide or gradually give way. In less than a second, a fraction of a second, the time it takes for light to cross a small room, a stellar core larger than the Earth compressed itself to a sphere roughly 12 miles across. The density that resulted was the density of an atomic nucleus, matter packed so tightly that the distances between particles, the ordinary spaces that make up most of what we think of as solid material, were entirely gone. Whatever the star had been, whatever shape and light and complexity it had carried for millions of years, none of it survived in the object now sitting at the center of that collapse. A new thing existed where the core had been, made entirely of neutrons, cooling rapidly, spinning faster than anything of comparable size has a right to spin. The outer layers of the star, falling inward at the moment the core gave way, struck this newborn object and rebounded. The shock wave that traveled back outward through the infalling gas was not alone in driving the explosion that followed. Neutrinos, produced in vast numbers during the collapse, streamed outward through the star with almost no resistance, and even the tiny fraction that were absorbed by the outer layers was enough. The energy they deposited was colossal, enough to accelerate billions of times the Earth's mass to speeds that would carry it outward across light years. The outer star exploded. The light from that explosion would eventually be visible across distances no human instrument had yet imagined. But it is not the explosion that concerns what happened next. It is the object left behind. The proto-neutron star sat at the center of the expanding blast, still cooling, still settling, still finding the configuration it would hold for billions of years. In those first seconds, it was not yet a neutron star in the quiet, steady sense. It was a seething sphere of nuclear density matter at temperatures measured in hundreds of billions of degrees, churning with convective currents that rose and fell through material no laboratory on Earth had ever produced. And it was spinning. Not slowly, not gently, but at a rate close to 100 rotations per second, perhaps several hundred, a small, extraordinarily dense object, turning faster than a turbine, its interior a roiling, turbulent dynamo primed for something extraordinary. Most neutron stars do not become magnetars. Most emerge from their formation with magnetic fields already strong by any ordinary measure, fields a trillion times more powerful than the one that holds a refrigerator magnet against a metal surface, and they go on to spin down slowly and predictably, their fields steady, their futures long and quiet. But for a small fraction, the conditions in those first seconds are different. The rotation is faster, the convection is more vigorous. The seed magnetic field that every neutron star carries from the time of its formation is caught by those churning currents and stretched and wound and amplified in a way that will not happen again in the star's entire subsequent life. The mechanism that accomplishes this works through the same general principles that generate magnetic fields inside the Earth and the Sun, though at scales of density, temperature, and speed that bear no useful resemblance to anything planetary or stellar in the ordinary sense. Differential rotation plays a central role, the inner regions of the proto-neutron star rotating at a different rate than the outer regions, shearing the magnetic field lines that thread through the interior and drawing them out into tight, wound configurations that multiply the field strength with each rotation. Convective flows, rising and falling through the star's hot interior, along paths shaped partly by that same rapid rotation, stretch the field further still, looping it, reinforcing it, where loops add together constructively, weakening it where they do not. The astrophysicists Robert Duncan and Christopher Thompson worked out the mathematics of this process in the early 1990s. What they found was that under the right conditions, primarily the combination of very rapid rotation and vigorous convection, a seed field of perhaps 10 billion to 100 billion Gauss could be amplified to 10,000 times that strength within seconds. The process they described is sometimes called the magnetar dynamo, and it is not a slow or gentle thing. It runs at full power, driving the field to its final strength, and then stops permanently as the proto-neutron star cools, its interior stratifies, and the convective currents that drove the amplification fade away. The window lasts perhaps 10 to 30 seconds. What the dynamo manages to build in that time is what the star carries for the rest of its existence, 10 to 30 seconds. A person falling asleep might take longer to close their eyes and find a comfortable position. But in those seconds, inside an object 12 miles across, made entirely of neutrons, spinning hundreds of times per second, a magnetic field is being wound to a strength the universe produces nowhere else by any known mechanism. The numbers that describe it, 10 to the 14th power, 10 to the 15th power, measured in Gauss, lose their weight when written down, so it is more useful to hold a single comparison. The strongest magnetic field ever produced in a terrestrial laboratory lasts for microseconds and measures perhaps a few million Gauss before the equipment that generated it destroys itself. The surface field of a magnetar is at least 10 million times stronger than that, and sustains itself not for microseconds, but for thousands of years. It is not a laboratory curiosity. It is a permanent feature of the object, woven into its structure, shaping everything that happens at its surface and in the space around it. The newborn magnetar does not announce itself in visible light. The explosion that accompanies its formation, the supernova, produces a light that outshines the entire galaxy of hundreds of billions of stars for weeks, and it is the supernova that draws the eye of any observer fortunate enough to witness it at the right moment. The magnetar itself is lost inside that glare, a tiny object radiating in X-rays and gamma rays, drawing on the energy of its own field in ways the outer stellar gas cannot interact with at that moment. What remains visible long after the supernova light has faded is the expanding shell of gas that the explosion drove outward, the supernova remnant. A supernova remnant grows slowly by the standards of a human life, and fast by the standards of most astronomical objects. The gas that was once the outer envelope of a massive star, now unbound and accelerating, spreads outward at thousands of miles per second into the surrounding interstellar medium. As it expands, it sweeps up that interstellar gas and compresses it, lighting it into glowing arcs and filaments that radio telescopes and X-ray observatories can detect across the galaxy. Over hundreds and thousands of years, the remnant grows from something the size of the solar system to a structure tens or hundreds of light years across, eventually thinning and cooling and blending back into the general texture of the galaxy. The magnetar sits at or near the center of that expanding shell, usually not quite at the geometric center, because the explosion that launched the gas was almost certainly not perfectly symmetric, and the kick imparted to the neutron star in the moment of core bounce typically sends it drifting slowly in some direction. Over the thousands of years of the magnetar's active magnetic life, it may travel a small distance from the center of the remnant before the remnant has grown large enough for the offset to be noticeable. Several magnetars have been found in this configuration. A magnetar, glowing in X-rays, sitting close to the center of an expanding shell of hot gas, with the elemental composition and structure of a core collapse supernova remnant. The association between them is not coincidental. The remnant and the magnetar were made together in the same event, the same second of core collapse, the same outward blast of neutrinos and shocked gas. The remnant is the visible record of the birth, expanding outward across the galaxy at its own measured pace, while the object that caused it spins and radiates, and gradually, over thousands of years, begins the long quieting of its field. To look at such a pairing, the magnetar in X-rays, the remnant in radio waves, both detected by instruments sensitive to light far outside the human visual range, is to see a single event unfolded across time. The remnant shows what the explosion was. The magnetar shows what the collapse left behind. Both are still present, still moving through the galaxy together, still telling the same story by different means. The gas in the remnant carries chemical information as well as light. A massive star that has spent millions of years fusing elements in its interior has built up layers of different compositions, a core of iron and nickel, shells of silicon and sulfur, and neon and oxygen and carbon above it, and the original hydrogen and helium of the outer envelope above those. When the explosion disperses these layers, it does not mix them perfectly. The remnant retains some of that layered structure, identifiable in the spectra of its light, and from that structure, astronomers can read something of what the progenitor star was like, how massive, how far along in its evolution, what proportions of heavy elements it had synthesized before it died. For the magnetar progenitors, the picture that emerges from these and other lines of evidence suggests stars of unusual mass. The threshold is thought to lie somewhere above 30 to 40 solar masses, stars that burned fast and hot and died young by stellar standards, spending only a few million years on the main sequence before their cores exhausted the material available for fusion. Whether a star above a certain upper mass limit might instead collapse directly into a black hole without leaving a neutron star at all is still an open question. The upper boundary on magnetar progenitor mass is not well constrained, and the precise conditions that determine whether a rapidly rotating core produces a magnetar or a slower spinning ordinary neutron star or no compact remnant at all are still being worked out. What the evidence does suggest clearly is that rapid rotation is essential. The dynamo needs it. A protoneutron star spinning once per second, a rate that would be considered fast for most astronomical objects, is not spinning fast enough to drive the convective amplification to magnetar field strengths. The rotation must be measured in milliseconds per period, hundreds of rotations per second, for the differential rotation and the convective geometry to work together effectively enough to amplify the seed field in the available time. How a progenitor star achieves that initial rotation rate is its own question. The angular momentum of the original stellar core is transferred inward during collapse, and if that core was rotating rapidly enough, perhaps because it was relatively young in its evolution, or because it had been spun up by a binary companion, or because of some combination of initial conditions not yet fully identified, the resulting protoneutron star inherits that rapid spin. There is something almost accidental about the conditions required. A slight difference in the core's rotation rate, a slightly different convective geometry, a seed field a little weaker or stronger, a collapse that proceeded differently in some small way, and the object that emerges from the supernova is an ordinary neutron star, radio loud and steadily slowing, its field strong but not extreme, its future long and predictable. The conditions that produce a magnetar are not common. They do not need to be. The 30 or so magnetars identified in the Milky Way and its nearest companion galaxies represent the full census of objects that happen to combine rapid enough rotation with vigorous enough convection in a window of seconds that opened and closed before most processes in the universe had time to register that it had occurred. Of that 30-second window, very little direct evidence remains. The dynamo that operated inside the newly born magnetar during those seconds left its signature in the field strength the magnetar carries, a field that can be estimated, though not directly measured, from the rate at which the magnetar's rotation is slowing down, the energy it radiates, and the characteristics of its outbursts. But the dynamo itself is gone. It ran for its allotted time and then stopped, as cleanly and completely as a process can stop, leaving no moving parts, no ongoing mechanism, only the field it built and the star that carries it. The protoneutron star, cooling now through its first minutes and hours, was still radiating an extraordinary quantity of energy. In the immediate aftermath of formation, neutron stars are among the hottest objects in the universe, with interior temperatures measured in hundreds of billions of degrees, and surface temperatures only somewhat lower. They cool by radiating neutrinos in enormous numbers, the same reaction that powered the initial burst of neutrinos during the collapse is still running at a lower level, a slow drain of thermal energy from the interior that will continue for thousands of years. The magnetic energy stored in the magnetar's field adds another source of heat, one that has no equivalent in ordinary neutron stars, keeping the magnetar's surface temperature elevated above what residual formation heat alone would sustain. But that is a feature of the mature magnetar's long life, not of its birth. In the moments after formation, the heat is everywhere and overwhelming, and the magnetic field is simply present, built, stored, waiting, the supernova remnant expanded, In the first hours and days after the explosion, it was still a dense, hot shell close to the star. Within years, it had grown to something the size of the solar system. Within centuries, it stretched across light years. The gas it swept up glowed as the shock heated it, and the light from that glow spread outward in turn, reaching the space around the expanding shell and illuminating the dust and gas of the interstellar medium in a faint aurora of scattered radiation. Inside the remnant, moving slowly away from its center, the magnetar cooled and settled. Its surface temperature fell from hundreds of billions of degrees to millions of degrees over its first 1,000 years, a dramatic cooling, though the temperatures it settled at would still be hot enough to fuse any material we could bring to them. Its rotation slowed as well, but only gradually, from hundreds of rotations per second to perhaps one or two, a slowing that took thousands of years and was driven partly by the energy radiated away in the magnetar's X-ray emission and partly by the torque of the magnetic field pushing against the thin plasma of particles in the surrounding space. The slowdown left a record in the timing of the magnetar's pulsations, and from that record, the age of the object could be estimated, checked against the age of its associated supernova remnant, and found to be consistent. That consistency, the magnetar timing age matching the remnant expansion age, is one of the cleaner pieces of evidence connecting what is seen now to what happened then. It is not a perfect measurement. Timing ages assume that the slowdown rate has been constant, and for magnetars, which are prone to sudden changes in spin and field behavior, that assumption is imperfect, but the broad agreement is reassuring. The magnetar and its remnant are the same age because they are the same event, seen from two different angles, the gas side and the compact object side of the same catastrophic collapse. Scattered across the inner Milky Way, a handful of these pairings have been found. A faint X-ray source pulsing slowly in the center of a wispy irregular shell of glowing synchrotron radiation, an X-ray source slightly offset from the geometric center of a thermal remnant, whose elemental abundances are consistent with a massive progenitor star. Objects found by systematic surveys of the galactic plane, located and identified and cataloged over decades by X-ray observatories, whose names are already fading from current use, replaced by newer instruments with better angular resolution and broader spectral reach. Each pairing is a separate birth, a separate star, a separate window of 30 seconds that opened billions of kilometers away and thousands of years ago. The progenitor stars themselves are long gone, not faded, gone, dispersed, their material now part of the expanding remnant, and eventually, as the remnant cools and slows and merges with the interstellar medium, part of the diffuse gas from which the next generation of stars will form. A massive star that lived for a few million years and ended in a supernova has contributed its substance back to the galaxy. The iron it made, the oxygen, the silicon, the carbon, all of it scattered across light years of space, thinning, mixing, traveling on trajectories that will eventually bring some small fraction of it into the collapsing cloud that makes a new star, a new system, and eventually perhaps a planet, with the right conditions for something more intricate still. The magnetar does not participate in that dispersal. It sits in the remnant's center, compact and dense and radiating, gradually slowing, gradually cooling, gradually losing the extreme field that defines it. Over 10,000 years, the field weakens as the electrical currents inside the star's crust slowly dissipate their energy, and the magnetar grows quieter, its X-ray luminosity declining, its outbursts becoming less frequent and less energetic, until eventually it is indistinguishable from an ordinary neutron star by any external measurement. The field is not gone, only weakened, settled to the ordinary strong field that a standard neutron star carries without drama. The magnetar phase is over. What remains is the same object, carrying the same mass and the same spin and the same internal structure, simply no longer driven to brightness by the extraordinary field it once held. This quieting is not an ending in any meaningful sense. The neutron star will persist for far longer than the magnetar phase lasted, longer than the progenitor star lived, longer than the galaxy in its current form will last. It will continue to slow its rotation, to cool its surface, to drift through the galaxy on the trajectory the supernova kick assigned to it. It will encounter no dramatic fate. It will simply continue, patient and dense and dark, a relic of an event that took less than a second and produced conditions that lasted 10,000 years. But the remnant, by that time, will be gone. The shell of gas that marked the supernova will have thinned and cooled and dissolved back into the interstellar medium within 10,000 to 100,000 years of the explosion, well before the magnetar phase even ends. There will be no visible record of the birth. The pairing that made the connection legible, the magnetar here, the remnant there, their ages consistent, their origin shared, will no longer exist. Only the neutron star will remain, unremarkable from the outside, carrying inside it the quiet ghost of a dynamo that ran for 30 seconds and then stopped. The interstellar gas moving into the space where the remnant was carries no memory of what passed through it. Gas is not in the business of memory. It cools and recombines and drifts, indifferent to the chemistry of what heated it, indifferent to the source of the shock wave that compressed it. Only the neutron star at the center of that dissolved cloud, drifting now on its slow path through the galaxy, no longer emitting much in any wavelength, holds any record of what it was. In the early universe, before the Milky Way had assembled into anything resembling its current shape, the process that makes magnetars was already running. The first generation of massive stars formed from hydrogen and helium alone, with no heavy elements to complicate their structure. And when those stars died, in millions of years rather than billions, because their simple composition drove them to burn faster and hotter, they collapsed into neutron stars, and when the conditions were right, into magnetars. The remnants of those earliest supernovae have long since been absorbed into the galaxy's gas. The neutron stars they left may still exist somewhere in the halo of the Milky Way, slowed to imperceptibility, dark against the dark. How many have there been over the full history of the galaxy? The question does not have a clean answer. The magnetar phase lasts 10,000 years. The galaxy is roughly 10 billion years old. If the rate of magnetar formation has been roughly constant, and if one estimates from the current population and the expected formation rate for massive star death, the total number of neutron stars in the galaxy that have passed through a magnetar phase at some point in their history could be in the millions, the vast majority now cold and quiet and invisible, indistinguishable from the broader population of neutron stars that never had magnetar strength fields at all. The 30 that are known are only the ones still bright enough in X-rays to be detected, still in their active phase, still carrying enough field to distinguish themselves from the ordinary. 30 points of light, or X-ray brightness, since none emit much in visible wavelengths, scattered along the intergalactic disk. Behind them, below them, spread across the galaxy in all directions, a vast invisible population of former magnetars, cooling slowly, spinning slowly, their brief extraordinary phase already over by millions of years. The supernova remnant that marked each one has dissolved. The gas that was once the outer layers of a massive star has rejoined the interstellar medium. The turbulent dynamo that ran for 30 seconds inside each collapsing core has left no trace except the field it built, and even that field is weakening, decade by decade, millennium by millennium, toward the unremarkable strength that all neutron stars share. What remains after everything is patience. The star that ended in a supernova spent millions of years building toward that final second of core collapse. The proto-neutron star spent 30 seconds amplifying a field that will last 10,000 years. The remnant spent tens of thousands of years expanding into the surrounding medium, then dissolved. And the neutron star, former magnetar, now simply dense and dark, will spend the remaining life of the galaxy drifting through space at the speed the birth kick assigned to it, unchanged and unchanging, long after every other trace of its origin has faded. The shell of gas from a magnetar's birth can still be seen when the object is young enough. It is irregular, brighter in some places than others, with filaments and knots where the shock wave encountered denser regions of the surrounding medium. Where the blast was more energetic, the shell is larger. Where the surrounding gas was thinner, it has expanded further. In some places, the remnant glows in radio waves, where electrons spiral around magnetic field lines and emit synchrotron radiation. In other places, it glows in X-rays, where the hot shocked gas radiates thermally. Astronomers working at wavelengths the human eye cannot register have mapped dozens of these structures across the galactic plane. Patient work, accumulated over decades, the images built from long observations and careful calibrations and instruments cold enough to detect photons one at a time. Within some of those remnants, an X-ray source glows faintly. It pulses slowly. Its spectrum carries the signature of a very hot, very small surface. Its brightness fluctuates in ways that no ordinary neutron star would, and its spin-down rate implies a magnetic field far stronger than the pulsars discovered earlier and cataloged in their thousands. These are the magnetars still young enough to be seen. Their remnants are still intact. Their fields are still high enough to drive the X-ray emission that makes them detectable. The birth event that made them, the core collapse, the 30-second dynamo, the neutrino flood, the expanding shock wave, is still written in the sky around them, readable to anyone with the instruments and the patience to look. The instruments have gotten better over the years, and they will continue to do so. The sky surveys have gotten more sensitive, and they will continue to do so as well. More magnetars will be identified, objects currently too faint, or too far, or too confused with background emission to be distinguished from the general sky. Each new identification will add a data point to the picture of how many there are, where they form, what their progenitors were like, and whether the dynamo model that Duncan and Thomson proposed in the early 1990s accounts for all of them, or whether there are other pathways to extreme field strength that the model does not include. Those are not questions with answers yet. They are questions being worked on, slowly and carefully, by people using instruments that gather light across wavelengths, spanning 20 orders of magnitude, waiting for signals that arrive without warning after traveling for tens of thousands of light years. The patience required is not so different, in spirit, from the patience of the remnant expanding outward at thousands of miles per second, building its visible record of the birth, waiting for something with eyes to look. For now, the remnants that are visible carry their record quietly. The gas moves outward. It slows as it sweeps up more of the surrounding medium. The brightness of the shock fades as the energy is spread across a larger and larger surface. The filaments and knots persist for a while, then dissipate, then are gone, and at the center the magnetar continues its slow rotation, its surface glowing in X-rays, its field still strong enough for one more season of brightness before the long quieting begins in earnest. The birth is over. The object it made remains. The remnant that recorded the birth is still expanding, still cooling, still carrying in its composition and its shape the signature of a massive star and a catastrophic collapse and 30 seconds of magnetic dynamo running at full power inside a sphere of nuclear matter, turning hundreds of times per second. All of that is still legible in the gas, in the light, in the slow timing of the X-ray pulses from the object at the center. It has been legible since the moment the collapse ended and the expanding shell began to glow. A message written in the language of physics, carried outward on the surface of a shock wave, still traveling, still fading, still there. The surface of a magnetar is made of crystal, not metaphorically, not approximately, a true crystal, geometric and ordered, a lattice of atomic nuclei arranged in precise repeating patterns, the way salt arranges itself or ice arranges itself, though nothing about the comparison does justice to what the material actually is. At the surface of this object, 20 kilometers wide and spinning in the dark between stars, the density of matter is already far beyond what any terrestrial rock or metal contains. The nuclei in that lattice are heavier than iron, neutron-rich in ways that matter on Earth never achieves, pressed into their geometric order by gravity so extreme that the word pressure loses its ordinary meaning. And threading through that crystal, invisible and immense, is a magnetic field whose strength no instrument on Earth has ever approached, and whose effect on the crystal it inhabits is the central fact of everything that follows. It is worth beginning at the surface, because the surface is the boundary between what can be observed and what can only be inferred. From thousands of light years away, telescopes in orbit gather the X-rays that stream from this object in quiescence, the steady glow of something hotter and more energetic than any comparable body in the known galaxy. What lies beneath that glowing surface is a matter of careful physics, of equations run through conditions no laboratory will replicate, of reasoning from the known behavior of matter pushed into unknown states. The inward journey is a slow one. Each layer reveals something stranger than the one above it, and each requires setting aside another ordinary intuition about what matter is and how it behaves. The crust of the magnetar, the crystalline outer shell, extends from the surface down through several kilometers of increasing density, and it is not uniform. Near the very top, atomic nuclei hold their ordinary shapes, bound together by the electromagnetic force in the presence of a gas of relativistic electrons moving through the lattice like a separate interpenetrating substance. The magnetic field at the surface, even here, is strong enough that electrons in that gas can only move in tight helical paths around the field lines, their orbits quantized in ways that change the electrical and thermal properties of the material fundamentally. Ordinary metals conduct heat one way. This crystalline crust, magnetized beyond any terrestrial analog, conducts heat differently along the field than across it, an anisotropy so pronounced it shapes the temperature map of the entire surface, creating hotter and cooler regions that have been detected as brightness variations in X-ray observations of real magnetars, faint patterns on a distant glowing sphere. Deeper in the crust, the nuclei grow heavier and more neutron-rich. Protons become increasingly scarce relative to neutrons because in this environment, the energetic cost of having too many protons forces them to convert, one by one, into neutrons through a process that releases neutrinos that carry energy away into space. The nuclei swell and deform, their boundaries growing less distinct, their interiors shading toward the surrounding sea of electrons, and lower still, of free neutrons. There is a depth at which this process reaches a specific threshold, a boundary as definite as a geological stratum, though no geologist will ever visit it. Below that depth, the nuclei have become so saturated with neutrons that free neutrons begin to leak out of them. They do not vanish. They gather between the nuclei, filling the space of the crystal lattice with a separate population of unbound neutrons, a quantum fluid existing in the same space as the crystal but obeying different rules. The lattice continues below this depth. The free neutrons begin. This transition is called the neutron drip point, and it marks the passage from the outer crust into the inner crust as precisely as any border crossed on a map. In the inner crust, the crystal lattice persists, but the neutrons that drip from the nuclei do not behave as ordinary particles. At the densities and temperatures present here, they form pairs. Two neutrons moving through the lattice couple together through a quantum mechanical attraction mediated by the nuclear strong force. And these pairs behave as a single entity that is no longer subject to the exclusion principle that governs individual neutrons. They flow without resistance. They share a collective quantum state, all pairs moving as one, a superfluid threading through the spaces of the crystal lattice the way a ghost moves through walls in old stories, present, real, physically significant, but passing through the solid material without friction, without scattering, without loss. This is not a laboratory phenomenon at low temperatures. The neutron superfluid of the Magnetars' inner crust persists at temperatures near 1,000,000,000 degrees Kelvin, stabilized not by the cold that stabilizes terrestrial superconductors, but by the crushing density of nuclear matter itself. The magnetic field that fills all of this, the field that makes this object a magnetar and not simply a neutron star, is not a uniform, simple thing. At the surface, where spin-down measurements allow direct inference, the field reaches a strength somewhere between 10 trillion and a quadrillion Gauss. A hospital imaging machine, which patients enter as a routine experience, operates at a field strength of perhaps 10,000 to 60,000 Gauss. The magnetar's surface exceeds even the strongest medical magnet by a factor of hundreds of millions. But the external field, the dipole field that broadcasts through space and leaves its signature in the slowing of the magnetar's rotation, is only part of the picture. Threading through the interior, wound around the star's core in closed loops that never break through to the surface, is a toroidal component of the field, a field that wraps inside the star in rings, the way a torus wraps around its own central hole, never escaping, never directly measurable from outside, but present and physically dominant in the star's interior. This internal toroidal field is thought to be stronger than the external dipole by a significant margin. Estimates place it at 10 to 100 times the surface field, somewhere in the range of 10 to the 15 or 10 to the 16 Gauss wound, inside the star like a vast invisible spring, exerting pressure outward against the crust in every direction. That pressure, the force the internal magnetic field exerts on the crystalline crust, is a Maxwell stress, a mechanical consequence of the field's geometry that is as real as the pressure of a hand pushing against a wall. The crust resists. It is, by the standards of neutron star matter, enormously rigid, 100 billion times more rigid than steel. If steel could be made from nuclear matter at densities no terrestrial forge approaches. But the internal field is patient. It does not push all at once. It evolves slowly. Through processes called Hall drift and ohmic diffusion, the field lines shifting and reorganizing through the crust over years and centuries, redistributing the stress across the lattice, loading some regions more than others, bending the crystal infinitesimally but continuously in directions it was not designed to accommodate. The crystal's breaking strain, the maximum deformation it can absorb before something gives, is finite. It has been estimated through simulations of nuclear matter at about 1 part in 10, which sounds large until it is compared against what the internal field eventually demands of it. The rigidity of the crust is not simply a passive resistance, it is itself shaped by the magnetic field. A neutron star with an ordinary magnetic field has a crust whose rigidity is determined mainly by the arrangement of nuclei in the lattice and the pressure of the electron gas. A magnetar's crust has all of that, plus the direct mechanical stiffening produced by the field. Field lines anchored in the crystal add their own tension to the structure, the way steel cables add tension to a bridge, making the whole assembly stronger along certain directions and weaker along others. This anisotropic rigidity means that the crust does not respond to stress the same way in all directions, and the eventual pattern of fracture, when it comes, will reflect the geometry of the field as much as the geometry of the lattice itself. Between the crust and the star's deepest interior lies a boundary that is itself a kind of transition in phase rather than composition. The inner crust gives way to the outer core, and in doing so, the crystalline lattice dissolves entirely. Below this boundary, there is no solid material, only fluid. The outer core of a magnetar is a liquid of neutrons and protons and electrons, all at nuclear density, all at temperatures that on Earth would constitute the hottest plasmas achievable. But here are simply the ambient conditions of an object in quiet, slow middle age. The neutrons in this liquid, like the neutrons in the inner crust, form superfluid pairs. They flow without resistance through the core, their collective quantum state extending through the entire volume, making the core, in the superfluid sense, a single connected entity, hundreds of kilometers in cross-section, though the star itself is only 20 kilometers wide. The quantum coherence length exceeds the physical scale, a fact that has no analog in ordinary condensed matter physics. The protons in the outer core do something complementary and equally extraordinary. Where neutrons form a superfluid, protons, which carry electric charge, form a superconductor. A superconductor is a material through which electrical current flows with no resistance whatsoever, and which responds to an external magnetic field in a specific way. The field cannot penetrate the superconductor uniformly. Instead, it is organized into discrete tubes of magnetic flux, each tube carrying a precise quantum of magnetic field, arranged in a regular array through the superconducting material, the way channels are arranged through a grid. In the magnetar's outer core, the enormous internal field is organized into these flux tubes, billions upon billions of them, microscopic in cross-section, each carrying its quantized thread of field through the superconducting proton fluid. The neutron superfluid flows around them. The flux tubes themselves are physically real structures, thread-like filaments of concentrated magnetic field embedded in a matrix that tries to expel them, held in place by the geometry of the field and the inertia of the star. This arrangement, superfluid neutrons and superconducting protons with their flux tubes, all at nuclear density, all at 1 billion degrees, all enclosed in a crystalline crust and bathed in a field of quadrillion Gauss, has consequences for how the magnetar rotates, and the consequences are detectable. When a neutron star's rotation rate is measured precisely over time, it is found to slow gradually, as the magnetic field breaking the spin carries angular momentum away into the surrounding space. But the measured spin-down rate does not always proceed smoothly. Occasionally, In magnetars and in ordinary pulsars, too, the rotation rate jumps. The star spins slightly faster for a moment, then resumes its normal deceleration. These jumps are called glitches, and they are small, a fractional change in spin rate of perhaps 1 part in a million, but they are real and repeatable, and they carry information about the star's interior. The glitch mechanism connects the superfluid interior to the solid crust. The neutron superfluid in the inner crust does not rotate as a rigid body the way the crust does. Instead, it stores angular momentum in an array of quantized vortices, tiny whirlpools of circulating superfluid, each carrying one quantum of angular momentum, arranged in a pattern whose spacing reflects the rotation rate. As the crust slows down under magnetic braking, the superfluid initially resists. It cannot slow down until its vortices move outward, and the vortices are pinned against the nuclei of the crystal lattice, held in place by an interaction between the nuclear strong force and the vortex cores. The pinning holds, the crust slows, the superfluid does not. The angular momentum difference between them builds. Stress accumulates at the pinning sites until suddenly the vortices unpin in a cascade. The superfluid transfers its excess angular momentum to the crust in a sudden step, and the star's observable rotation rate increases by that small but measurable fraction. The process then begins again, slowly, over months or years, building toward the next glitch. In magnetars, this already complex mechanism is further tangled with the magnetic field's influence on both the superfluid and the flux tubes in the superconducting core. The flux tubes and the vortices interact, and the vortex motion needed to allow the superfluid to spin down is coupled to the motion of flux tubes, which in turn affects the evolution of the magnetic field over time. The magnetic field's decay, the crust stress accumulation, the superfluid's angular momentum storage, and the timing of glitches are not independent processes. They are coupled components of a single evolving system, and in a magnetar, the coupling is tighter and more energetic than in any other known neutron star. The surface of the magnetar, viewed from the only vantage available, from great distance, through telescopes sensitive to X-rays, glows at temperatures between roughly 3 million and 7 million Kelvin. This is hot by any ordinary measure. The sun's surface is near 5,500 degrees Kelvin. The magnetar's surface is 1,000 times hotter. From a surface only 20 kilometers across, this temperature produces a luminosity in X-rays that in quiescence, without any burst or flare, exceeds the total light output of the sun by a factor of 10,000. An object the size of a city, glowing 10,000 times brighter than the star at the center of the solar system, in light invisible to the eye, but real to every physical measure. The origin of that heat is what distinguishes a magnetar from an ordinary neutron star of similar age. A neutron star formed in a supernova retains a great deal of heat from its formation, and that heat radiates away slowly over thousands and millions of years, the surface cooling as the interior temperature decreases through neutrino emission. By the standard cooling models, a neutron star several thousand years old should have a surface temperature of around 1,000,000 Kelvin, declining further as it ages. Magnetars of similar estimated age are measurably hotter than this. The excess heat cannot come from residual formation warmth alone. The cooling models are well constrained, and the discrepancy is real. What supplies the additional heat is the magnetic field itself. Inside the magnetar, the enormous field stores energy the way a compressed spring stores energy, not in any metaphorical sense, but in a direct thermodynamic one. The field is not perfectly stable. It evolves through the same Hall drift and ohmic diffusion that redistributes stress in the crust, the field lines shifting slowly as the electrical currents that maintain them dissipate their energy into heat. Ohmic dissipation is the process by which electrical resistance converts current into thermal energy. It is the same process by which a light bulb filament glows when current passes through it. In the magnetar's crust, where the current densities are immense and the field energy is enormous, ohmic dissipation releases heat continuously into the crust, which then conducts outward to the surface and radiates away as X-rays. The field is, in effect, a vast energy reservoir that powers the star's luminosity, not through rotation, the way a pulsar powers its emission, but through its own slow decay. The magnetar is sustained by its own undoing. The rate of this decay is not the same everywhere in the crust. Hall drift, the dominant field transport mechanism in the outer crust, moves the field in a systematic way that depends on the local electron density and field strength. Where the electron density has a gradient, the field is carried preferentially in one direction, concentrating field energy in some regions and depleting it in others, building small-scale structure in the field at the cost of the large-scale dipole. This concentration of field energy in small patches of the crust accelerates the local ohmic dissipation there, creating local hotspots on the surface that are sometimes visible as bright regions in X-ray images of magnetars, maps of the heat flowing outward from a field evolving inside. The geometry of the field at the surface is not a perfect dipole. Real magnetars show evidence of significant contributions from higher-order field components, quadrupole terms, octupole terms, that produce field structures more complex than a simple bar magnet. Some of this complexity is inherited from the birth dynamo, which operated in a turbulent, asymmetric environment and would not have generated a perfectly symmetric field. Some of it develops over time through Hall evolution, which has a tendency to generate small-scale structure out of large-scale order. The magnetar surface is therefore magnetically irregular, patches of stronger and weaker field, regions where field lines emerge nearly perpendicular to the surface, and regions where they emerge at oblique angles, a geography that shapes both the heat distribution and the pattern of emission that telescopes detect. Above the surface, extending outward into the space around the magnetar, is the magnetosphere, a region of extremely dense magnetized plasma that the field controls completely, where matter cannot move independently of the field lines because the magnetic energy density exceeds the kinetic energy density of the plasma by many orders of magnitude. The magnetosphere of a magnetar is not empty. It is filled with electrons and positrons, the products of pair creation driven by the intense curved magnetic field, and with radiation, X-rays scattering off electrons, photons being absorbed and re-emitted, a complex luminous environment that astronomers are only beginning to map with dedicated X-ray and soft gamma-ray observatories. The magnetosphere is where the magnetar's internal physics becomes external signal, where the currents twisted by the evolving internal field emerge as observable emission, where the heat conducted from the crust radiates outward, where the consequence of everything happening inside the star becomes, in a limited but real way, measurable. Within the magnetosphere and extending from the surface in a region called the corona, currents of charged particles flow along the field lines, twisted by the internal field's evolution below. These currents heat the corona to temperatures higher even than the surface, possibly several tens of millions of Kelvin in active magnetars, producing a hard X-ray component of the emission that cannot be explained by the surface thermal glow alone. This corona is observed in real magnetars during periods of enhanced activity, its spectrum and luminosity changing over timescales of weeks and months as the underlying field evolves. It is a direct bridge between the interior physics and the observable universe, a thin luminous shell around the crystal and the superfluid and the billion-degree quantum fluid inside, carrying the imprint of everything that has happened to the star since its violent birth. The internal toroidal field, the component wound in closed rings inside the star, invisible from outside, has a specific mechanical effect on the crust that is worth tracing carefully. A toroidal field inside the star exerts an outward pressure on the crust, the way air pressure inflates a balloon, but because the field is wound in rings whose geometry is not spherically symmetric, the pressure varies across the surface of the crust. Where the field pressure is greater, the crust is pushed outward. Where it is less, the crust sits at a lower equilibrium. This differential pressure gives the magnetar a slight deformation from a perfect sphere, an oblateness, or more precisely, a more complex non-spherical shape, reflecting the geometry of the wound internal field. The deformation is small. It is measured in fractions of millimeters across a 20-kilometer sphere, but it is real, and it has implications. A non-spherical neutron star rotating in space radiates gravitational waves, ripples in space-time that carry energy outward at the speed of light. The waves from even the largest theoretically possible magnetar mountain are too faint to detect with current instruments, but they are there, and the next generation of gravitational wave observatories may be sensitive enough to find them, a new way of reading the magnetic structure of an object that cannot be visited or imaged in any traditional sense. The surface of the magnetar, the crystalline crust, sits under all of this. Above it, the magnetosphere glows and crackles with twisted currents and pair-created plasma. Below it, the neutron drip point marks the beginning of the inner crust, where free neutrons thread the lattice in a frictionless quantum fluid. Below that, the lattice dissolves and the core begins, neutron superfluid and proton superconductor, and magnetic flux tubes arranged in their regular array, all rotating together and slightly separately, all coupled to the spin and the field and the heat flow of the whole structure. And through all of it, from surface to core, the magnetic field, toroidal deep inside, complex multipolar near the surface, dipolar at the large scale, evolving slowly through Hall drift and ohmic decay, powering the luminosity by its own undoing, and pressing against the crust with the slow, patient force of a spring that has been winding for thousands of years. The crust holds. For now, it holds. Its breaking strain is finite, and the field's pressure is real, and the drift of the field lines through the crystal lattice over years and centuries, redistributes that pressure in ways the lattice cannot perfectly accommodate. Some regions of the crust are bent further than others. Some are closer to their yield point. The crystal is not failing yet, but it is not perfectly still either. It is under stress, the way old stone arches are under stress, carrying their load along paths that took centuries to find equilibrium, holding because the geometry of the forces and the strength of the material are for now precisely enough matched. In the deep interior, the neutron superfluid does not know or care about the stress in the crust above it. It flows in its frictionless loops, its vortices pinned to the lattice above in ways it cannot escape, its angular momentum stored and building. The flux tubes in the superconducting proton core move as slowly as the field they embody, each carrying its quantum of field through matter that wants to expel it, but cannot yet, because the energetics are not yet favorable, because the geometry is not yet right. All of these slow processes are coupled. All of them are building towards something, in the same way that geological stresses build without intention and without schedule toward a release that cannot be predicted to the day or the hour, but cannot, in the long run, be avoided. The magnetar rotates once every few seconds, its period measurable from Earth as a precise repeating pulse of X-ray brightness. The period is slowly lengthening, the field's braking carries angular momentum outward, and the star, over thousands of years, is spinning down. Each rotation carries the asymmetric surface brightness around once more, the slightly hotter and slightly cooler patches of the crust describing a slow circle in the dark. The magnetosphere turns with it, the field lines sweeping through the surrounding space. The internal structures, superfluid and flux tubes and crystalline lattice, all rotate together, almost together, each at its own slightly different rate, the coupling between them a slow and continuous negotiation of angular momentum. Deep in the core, far below the crystalline surface, and the neutron drip point, and the dissolving boundary where solid gives way to fluid, the superfluid neutrons flow in their quiet, frictionless currents, indifferent to the temperature that would destroy any terrestrial material, indifferent to the field that threads them, carrying their angular momentum in vortices pinned to geometry, rather than to any physical surface, flowing without loss through a volume of space that by every ordinary measure should not be able to sustain them. The magnetar hangs in the space between stars, 20 kilometers from one side to the other, its surface blazing in X-rays that stream away at the speed of light. Its crystal holds, its superfluid flows, its field winds invisibly inward through the core, pressing outward against the surface with forces that will, over centuries, find the places where the crystal is least able to resist. The object is, in its quiescence, a system in slow, delicate tension, an architecture of states of matter whose coexistence seems, at the scale of ordinary intuition, barely possible, yet which persists here because the physics of extreme density and extreme field simply allow no other configuration. All of these layers, stacked inside 20 kilometers, occupy the same small volume of space: the crystalline outer crust, the neutron drip boundary, the inner crust with its superfluid threading, the lattice, the transition to the liquid core, the superfluid neutrons, the superconducting protons with their ordered flux tubes, all of it enclosed in a magnetic field that represents more energy than the sun releases in years of steady burning. The surface glows, the interior flows, the field holds all of it in its geometry, the way a structure holds its own weight, invisibly and without sound, in the darkness between the stars. And it is in that darkness, in the quiet between events, that the full strangeness of the object is most apparent. Not in its bursts or its flares. Those are consequences, the downstream results of what accumulates inside. The strangeness is here, in the layered coexistence of crystal and superfluid and superconductor, in the way quantum states that require extreme cold to achieve in a laboratory persist here at 1,000,000,000 degrees because the physics of nuclear density replaces the physics of temperature as the stabilizing force. A city-sized object containing more mass than the sun, its interior a library of extreme states that nowhere else in the reachable universe exist in quite this arrangement, its surface glowing in light no human eye can see, its field shaping the very geometry of the atoms it touches. No two of its layers obey the same rules. The crystal follows the rules of nuclear condensed matter, its rigidity shaped by field and density, and the quantum exclusion of its electrons. The superfluid follows the rules of quantum fluid mechanics, its vortices carrying angular momentum in discrete steps, its coherence extending across the entire volume. The superconducting proton fluid follows the rules of paired quantum states in a dense medium, its flux tubes organized in the regular array the field geometry demands, and the field itself follows the rules of magnetohydrodynamics in a regime where every parameter is at or beyond its known boundary, a single magnetic structure threading through three distinct phases of matter simultaneously, coupling them to each other, making the whole object respond as a connected system rather than as a collection of independent layers. In the deep interior, where the superfluid neutrons move in their slow, frictionless vortex-threaded currents, there is no light. The neutrons do not emit. The flux tubes do not glow. The currents leave no trace that travels outward, only the heat they carry, diffusing slowly through the crust toward the surface, where it finally emerges as the X-ray glow that crosses thousands of light years to reach the instruments that measure it. What happens at the core is known through inference alone, through the equations that describe matter at nuclear density, and through the faint signals, the glitch timing, the luminosity excess, the hard X-ray spectrum that the interior writes on the surface for observers far away to read. The frictionless currents flow on. The crystal holds for now. The field winds through the interior in its invisible rings, and the whole small, dense, extraordinary object turns in the dark, once every few seconds, radiating the slow dissipation of its own magnetic energy as X-rays that travel away from it in every direction into the space between the stars, carrying the information of what it is and how it is built to anyone far away with instruments fine enough to read it and patient enough to wait. Deep inside the crust of the magnetar, something is bending, not quickly, not with any sound a human instrument could register at this distance. The bending has been happening for years, perhaps for decades, in a lattice of atomic nuclei arranged in crystalline order at densities no laboratory on Earth has ever reproduced. The material is cold by neutron star standards, though cold here means temperatures that would vaporize any ordinary matter in an instant. The lattice holds its geometry, it holds its order, and all the while, invisible and immense, the magnetic field threading through it from below presses outward like a tide that never fully retreats, accumulating in the crystal structure as a tension too slow to watch and too deep to measure directly from the outside. This is where the story of a starquake begins, not in the burst, not in the gamma rays spreading outward at the speed of light, not in the moment the crust finally yields, but here in the long patience of nuclear matter holding against a force it cannot ultimately withstand. The lattice itself is nothing like the crystal of a gemstone or the metal of a structural beam, though the word crystal is the right one. It is composed of atomic nuclei, each one far heavier and more neutron-rich than any nucleus found in ordinary matter, arranged in a repeating geometric structure that extends across the full thickness of the magnetar's outer shell. That shell is perhaps a kilometer deep. In some places it may be thicker. The nuclei sit in fixed positions, separated by distances incomprehensibly small, bound in place by electromagnetic forces, and surrounded by a sea of electrons moving at close to the speed of light. The whole structure is rigid in the way only matter under extreme pressure can be rigid, resistant to deformation, not because it is fragile, but because the forces holding its geometry are enormously strong, 10 times stronger by some estimates derived from simulations of nuclear matter than the strongest steel humanity has ever produced. And yet, steel also bends. Steel also has a limit beyond which it does not spring back, but breaks. The magnetic field inside the magnetar has geometry of its own. The field that is measurable from outside, the field that makes the star's rotation slow over time as energy bleeds away into the surrounding space, is only part of the picture. Inside the body of the star, wound through its interior in closed loops that never break through to the surface, there is a second component of the field, a toroidal structure wrapped like invisible rings through the star's equatorial interior. This internal field may be far stronger than the one facing outward. It cannot be measured directly. Its presence is inferred from the way the star behaves, from the slow drift of magnetic energy outward through the crust, from the way heat leaks unevenly across the surface, from the timing of outbursts that follow patterns no simple dipole field would produce. Over years and centuries, the geometry of this interior field shifts. The process is called Hall drift, and it is not violent. It is the slow migration of electrical currents through the conducting material of the crust, each small redistribution altering the stress state of the lattice a little further. The way shifting weight on a structure changes, where the load bears most heavily, not at once but over time. The stress builds in localized regions. It does not build uniformly across the whole crust. Just as geological faults on Earth concentrate strain along specific boundaries, where rock types meet, or where the crust is thinnest, the Magnetars crust develops regions of elevated stress, where the magnetic geometry makes the local Maxwell tension, the force per unit area that a magnetic field exerts on the material anchoring it, highest. These regions are invisible from the outside. The star does not change its appearance as the stress builds. It continues to rotate, once every few seconds, its surface blazing in X-rays, its emission varying slightly from one rotation to the next, in ways that are cataloged and measured by observatories that have been watching specific magnetars for years. The star carries its accumulating tension without announcement, and then the lattice yields. The moment of yielding is not the slow process that preceded it. The fracture propagates through the crust at the speed at which shear waves travel through nuclear matter, fast by any ordinary measure, though not instantaneous. A fault line opens. A region of crystal that has been held in one geometric configuration for years slips into another, the nuclei, in one section of the lattice, shifting relative to those in the neighboring section by distances that are, on human scales, not even measurably small. But in nuclear matter, even a small slip is enough. The magnetic field lines that have been anchored in the crust on either side of the fracture were held in fixed positions by the rigidity of the lattice. They were under tension. When the lattice fractures, those field lines are displaced, pulled out of alignment in a fraction of a second after years of being fixed in place. The displaced field lines do not stay displaced quietly. They are under tension too, like a bowstring that has been pulled to one side and then released. The displacement launches a pulse, a wave that travels along the magnetic field line upward from the surface of the star into the magnetosphere, the region of magnetized plasma that surrounds the magnetar out to distances of thousands of kilometers. The wave is an Alphen wave, a disturbance that propagates along magnetic field lines, the way a vibration travels along a taut wire, except that here the medium is not wire, but a magnetized plasma, and the wave travels at a velocity that approaches the speed of light, because the magnetic field threading the plasma is so strong that the signal velocity is close to its maximum possible value. The wave carries the energy of the fracture with it. It rises through the magnetosphere in the time it takes light to cross a few thousand kilometers, a small fraction of a second. In the magnetosphere, that energy does not simply pass through and escape. The plasma environment of a magnetar is unlike any other plasma in the universe. The magnetic field is strong enough that the plasma cannot move across field lines without enormous resistance. Particles are threaded onto those lines and constrained to move along them. The Alphen wave encounters this constrained relativistic plasma and drives instabilities in it, cascades of particle acceleration and pair creation in which electrons and positrons are born from the energy of the field and immediately radiate as they interact with the field around them. The radiation that emerges from this process spans a wide range of wavelengths, but its peak lies in the X-ray band and the soft gamma-ray band, the same band in which magnetars are observed in quiescence, but now magnified, in the case of a major event, by factors of many thousands above the quiescent level. The burst has begun. Short bursts from magnetars last from fractions of a second to several seconds. They are detected by space-based X-ray and gamma-ray observatories, which record the incoming photons as a sharp rise in count rate against the steady background of cosmic emission. Most bursts go unremarked in popular accounts of astronomy. They are real events, real fractures in real stellar material. But their energy, though vast by any terrestrial standard, is on the lower end of the magnetar energy budget, releasing between roughly 10 to the 37th and 10 to the 41st units of energy in the physical measure astrophysicists use for such quantities. They are, in effect, the microseisms of the magnetar, small yieldings, local fractures, the crust releasing stress at its weakest points before the larger ruptures that accumulate over longer timescales. The giant flare is different. A giant flare is what happens when a large region of the crust fractures all at once, or in rapid sequence, releasing an amount of energy that places it in a category almost entirely its own. On the 27th of December in 2004, a magnetar designated SGR 1806-20 released a giant flare. The event was measured by several spacecraft. It began with an initial spike lasting approximately 0.2 of a second. In that interval, shorter than the time between a human heartbeat and the next, the energy released was equivalent to what the sun produces across roughly 250,000 years. The figure does not become more comprehensible by repetition, but it is worth sitting with quietly for a moment. A single object, 20 kilometers across, releasing in 0.2 of a second the same amount of energy as a star would produce across 250,000 years of continuous shining. The burst from SGR 1806-20 was located somewhere between 28,000 and 50,000 light-years from Earth in the inner part of the Milky Way. The gamma rays it released traveled across that distance at the speed of light and arrived here in the final weeks of that year. When they arrived, they were still energetic enough to ionize the upper layers of Earth's atmosphere, the night side ionosphere, the region where X-rays and gamma rays from above strip electrons from neutral atoms and create a faintly conducting layer. This effect was measured. Instruments designed to monitor the state of the ionosphere recorded the disturbance clearly, and the timing matched the arrival of the flare's leading edge. A magnetar in the far interior of the galaxy, tens of thousands of light-years away, briefly and measurably altered the electrical environment of the air above the Earth's night-side hemisphere. The distance had been enough to reduce the flare's intensity to something far below any danger threshold. At a fraction of that distance, 10 light-years, or even 100, the effects on any planetary atmosphere would have been severe. But at the distance it arrived from, it was merely a measurement, a pulse in a detector, a trace on a recording that confirmed the numbers were not theoretical estimates, but real quantities attached to real events. After the initial spike came the tail of the flare. The tail lasted several minutes. During the tail, the magnetar continued to radiate at a level far above its quiescent output, and as it rotated, once every 5 seconds, the emission modulated with its rotation period, the way a lighthouse beam sweeps past periodically, because the emitting region was not distributed uniformly over the star's surface, but concentrated in a structure that rotated with the star. This pulsing tail allowed observers to study the geometry of the event in detail, and within the tail they found something else, a more subtle modulation, a pattern of oscillations superimposed on the rotational pulse. These oscillations were quasi-periodic. They repeated at frequencies ranging from just under 20 cycles per second to over 1,000 cycles per second. They persisted throughout the tail and faded as the flare subsided, and they represented something that had never been clearly measured before, the sound of the neutron star ringing. The analogy to a ringing bell is not merely poetic. When a bell is struck, the impact sets the material of the bell vibrating in a set of natural modes determined by the bell's shape, size, and composition. Different modes ring at different frequencies. The spectrum of those frequencies is a fingerprint of the material. Measure the frequencies precisely, and you can work backward to determine properties of the bell, how rigid it is, how it is shaped, how its mass is distributed, without ever being able to touch or sample it. The neutron star, struck by the starquake, vibrates in analogous modes. Its natural oscillation frequencies are set by the elasticity of its crystalline crust, the geometry of its internal magnetic field, and the properties of the matter in its deep interior. The quasi-periodic oscillations detected in the tail of the 2004 giant flare and in the tails of other large flares from other magnetars are the frequencies of those natural modes, propagating outward as modulations in the emitted radiation. This field of study is called magnetar seismology, and it is, in its way, as patient and as careful as the seismology practiced by geologists who study the Earth. The Earth's interior cannot be sampled directly below a certain depth. Everything known about the structure of Earth's core, its liquid outer layer, its solid inner region, the boundary between them, was inferred from the way seismic waves travel through and reflect from structures that no drill has ever reached. The same logic applies to the magnetar. Its crust cannot be sampled, its interior will never be visited, but the vibrations it produces when disturbed carry information about its internal structure encoded in their frequencies, and that information can be extracted with care. The oscillation frequencies observed in the 2004 flare include one near 18 cycles per second, others near 30 and 90, and near 150 cycles per second, and several at frequencies over 1,000 cycles per second. Different theorists, working with different models of crust rigidity and different assumptions about the geometry of the internal magnetic field, produce different predictions for which oscillation modes should appear at which frequencies. The data from the flare allow those models to be tested and refined. Over the years since the flare, the comparison between observed and predicted frequencies has narrowed the range of physical models consistent with the data, excluding some and lending support to others, in the way that any precise measurement narrows the space of possibilities. A second giant flare has since been analyzed in similar detail. Others have been detected with less complete data. Each event adds another set of oscillation frequencies to the catalog, another set of constraints on the models, another trace of the neutron star's internal structure, pressed into the record by the energy of the quake that set it ringing. The star quiets after the flare. This process is itself slow on human timescales, though fast by astronomical ones. The initial burst lasts fractions of a second. The pulsing tail lasts minutes, but the aftermath lasts longer. In the weeks and months following a large burst, the surface temperature of the magnetar is measurably elevated above its pre-burst level. The heating comes partly from the energy deposited in the crust by the fracture process, and the electromagnetic energy dissipated close to the surface. The magnetar radiates this excess heat away gradually, and observatories that return to the source over time can track the slow decline of its surface temperature, fitting the decay to models of how heat diffuses through the crust and escapes from the surface. These cooling curves are another source of information about the internal structure. Different models of the crust's thermal conductivity predict different rates of cooling, and the observed rate constrains the real properties of the material. During this same interval, the magnetar's rotation is disturbed. Major outbursts are often associated with a sudden change in the star's spin rate, a glitch, in which the rotation either speeds up slightly or changes its rate of slowdown in a way that is detectable through the precise timing of the pulses arriving at distant observatories. Some of these timing events are associated with the transfer of angular momentum from the star's superfluid interior to its solid crust. Others may reflect changes in the torque applied to the crust by the reconfigured magnetic field. The magnetar carries the record of the event in its rotation for months or years afterward, its timing gradually settling toward a new baseline that incorporates the small change the quake produced. The crust itself, after the fracture, is not in the same configuration it held before. The slip along the fault plane has permanently shifted the geometry of the lattice in that region. The field lines anchored in the crust are now in a slightly different arrangement. The local stress in the region of the fracture has been partially relieved, but not everywhere. Other regions of the crust, where the stress had not yet reached the breaking point, are still accumulating their tension. The Hall drift continues. The ohmic diffusion continues. The interior field continues its slow evolution. What has changed is one specific region's contribution to the total stress state of the crust, and the star proceeds with that small adjustment made, carrying its remaining tension forward through the years. It is not always clear from outside whether a given burst represents a single large fracture, a cascade of smaller fractures triggered in sequence, or some combination of processes involving the magnetosphere as well as the crust. The observational signatures of different mechanisms can overlap. A magnetar that undergoes a period of elevated burst activity, producing many short bursts in succession over days or weeks, a state called an outburst, may be experiencing a sequence of smaller fractures as a region of high stress yields in stages rather than all at once. Or the magnetosphere itself may be destabilized by a smaller initial event and produce additional emission through purely plasma processes without further crustal fracture. Separating these possibilities requires detailed observations across multiple wavelengths and careful modeling, and the answers in many specific cases are not yet settled. What is clear is the energy budget across the full range of events. Short bursts, large bursts, and giant flares represent a continuum spanning many orders of magnitude in total energy released. Each event, whatever its size, draws on the same reservoir, the magnetic field itself, slowly decaying, converting its stored energy into radiation through the mechanical and electromagnetic processes that the fractures and their aftermath set in motion. The active lifetime of a magnetar, the period during which its field is strong enough to power this kind of activity, is estimated at around 10,000 years. Over that interval, the field decays from its initial extreme strength toward the level of an ordinary neutron star. The energy released in bursts and flares over that lifetime represents a portion of the total energy stored in the field, a portion that, summed across all events over all those thousands of years, is immense but finite, a budget being drawn down one fracture at a time. There is something in this that belongs to the long rhythms of astronomy, the processes that operate across timescales, too large for any human measurement program to span, but that can be understood from careful study of populations and individual events. The magnetar active phase of 10,000 years is brief by stellar standards, a bright interval between the turbulent birth of the star and the quieter existence that follows, when the field has decayed to ordinary levels, and the quakes and flares cease, and the neutron star enters a long, calm old age. The bursts that mark the active phase are not random. They are the expressions of a physical process playing itself out, stress accumulated, stress released, crust resettled, field redistributed, in the same logical sequence that governs every physical system, that stores energy and releases it in discrete events. The star does not choose its timing. The crust does not negotiate with the field. The fracture happens when the local stress exceeds the local yield strength and not before, and the energy released reflects how much stress had accumulated in that specific region of the crust at that specific moment. There is a precision to it that is impersonal and complete. The lattice bends until it does not bend further, and then it breaks, and the field lines move, and the wave rises into the magnetosphere, and the gamma rays depart at the speed of light in all directions through the surrounding space, carrying with them the record of what happened in the crystal of a star, 20 kilometers wide in the far interior of the galaxy. The gamma rays from the 2004 giant flare crossed a distance that light takes between 28,000 and 50,000 years to cover. They arrived at the detectors of spacecraft in orbit and left their impression on the ionosphere and continued outward past the solar system into the space beyond, where they will travel for a very long time. The energy they carry is real and finite and exactly as large as the measurements say. The star that released them continues to rotate, once every 5 seconds, cooling slowly, its crust resettling, its field still strong, but a fraction weaker than it was before the flare, the process of decay continuing on its own, unhurried schedule. The quasi-periodic oscillations detected in the flare's tail, those faint rapid modulations in the fading X-ray glow, lasted only minutes. They carried information about the elastic properties of matter at nuclear density, about the geometry of a magnetic field too strong to be reproduced anywhere in the solar system, about the internal structure of an object whose surface no physical probe will ever visit. That information was encoded in frequencies, and the frequencies were measured, and the measurements were recorded, and the work of interpreting them continues in the way that careful science continues, slowly, without guaranteed answers, but with results that are more useful for what they exclude than for what they confirm, with each new event adding a small but real constraint to the picture. The crystalline lattice of the magnetar's crust, wherever it is still intact, holds its geometry in the dark. The stress continues to build in whatever regions of highest local tension remain, invisibly and without announcement. The interior field drifts, degree by imperceptible degree, toward a new configuration. Somewhere in the part of the crust that has not yet yielded, a region is approaching its limit, not yet there, not yet at the point where the local stress exceeds what the lattice can hold, but moving toward it across time in the only way physical processes move, one moment at a time, at whatever pace the physics permits. The magnetar does not wait. It is not patient in the way that living things are patient. It simply proceeds, as all things made of matter and governed by forces proceed, through the states available to it in the order that the laws of physics prescribe. The crust will bend until it breaks, the field lines will move, the wave will rise, the radiation will depart, and afterward, as always, the long quiet of cooling and resettling will follow, the surface temperature declining week by week, the rotation returning toward its baseline, the lattice holding its new configuration against the continuing slow pressure of the interior field. This is the rhythm of the active magnetar, not constant, not predictable in its specific timing, but regular in its underlying logic, stress accumulated in silence, released in an instant or a fraction of an instant, the aftermath measured in warmth that fades over weeks and months, the record written in the slow evolution of a spin rate that has been precisely timed for years. Each cycle draws the star incrementally closer to the end of its active phase, the 10,000-year window in which the field is strong enough to drive these events. When the field decays past a certain threshold, the quakes will cease, the surface temperature will fall, the bursts will stop. The star will still exist, dense, compact, rotating in the dark, but it will do so quietly, without the flares and outbursts that marked its active youth, carrying only the faint residual warmth of a once enormous field in a crust that no longer has the stress to break. For now, the field is still strong, the crust still holds regions of accumulated tension. Somewhere in the inner galaxy, a magnetar that has not yet been catalogued is proceeding through its active phase, its interior field drifting, its crust bending, its surface blazing in X-rays at a luminosity that dwarfs the sun by thousands of times, its rotation ticking steadily in the dark at a period of a few seconds. It will produce a burst, perhaps it already has, and the gamma rays are already traveling outward across the galaxy toward wherever they happen to be going, crossing light years of interstellar space at the speed of light, carrying the record of a fracture in a crystalline lattice of nuclear matter. That record will take a long time to arrive anywhere. Most of it will arrive nowhere, will simply continue outward through interstellar and then intergalactic space, growing fainter with distance, eventually dispersed below any detectable threshold, the energy real and present, but too thinly distributed to register on any instrument. A small fraction of it may arrive at an observatory. If it does, it will be measured, and the measurement will be added to the record, and the record will continue to be studied with the patient attention that this kind of science requires. The magnetar, when the burst has passed, cools. The surface temperature, elevated by the event, begins its slow decline, the excess heat diffusing outward through the crust in the way that heat diffuses through any solid material, flowing from warmer regions to cooler ones, spreading and thinning as it goes, until the surface is radiating again at close to its pre-burst level, warm by any ordinary measure, still blazing in X-rays, still carrying within its 20 kilometers of radius more matter than the sun, still rotating, still proceeding through the long arc of its active lifetime, 1 second at a time, the crust still holding, the field still pressing outward, the lattice still bending in the dark. On the 14th of April, in the year 2020, 2 signals arrived at Earth at almost exactly the same moment. One was a pulse of radio waves, lasting only a fraction of a second, bright enough to register on instruments halfway across the country from one another. The other was a burst of X-rays, harder and more energetic, recorded simultaneously by 3 separate telescopes in orbit. They had traveled together across the galaxy, side by side at the speed of light, for roughly 30,000 years. They arrived together, and in arriving together, they answered something. The source was a magnetar, a known one already catalogued, already watched. From a position within the Milky Way, in the direction of the constellation Aquila, a star only 20 kilometers across had released both signals in the same breath, radio and X-ray, together, not separately, not in sequence, together, as though the two were aspects of one single event, which they were. For years, astronomers had been detecting fast radio bursts, short, brilliant flashes of radio energy arriving from deep beyond the galaxy, from distances of hundreds of millions or billions of light years, each one lasting only milliseconds, each one carrying more energy than the sun releases in days or weeks. They had no confirmed source. Magnetars were among the leading possibilities, but the distances were too great to verify, and no burst had ever been caught with an X-ray counterpart close enough and clear enough to name. This one was. This one at last was close enough to check. The radio pulse was called FRB 200428. The FRB stood for Fast Radio Burst. The numbers for the date? It was the first of its kind to be pinned to a known object in a known place with certainty, and the picture it completed had been building for a long time. The burst was not as bright as the extragalactic ones. By the standards of what had been arriving from the far universe for years, it was modest, but it was the right shape. It had the right duration, the right spectral character, the right X-ray companion, and it came from a magnetar, from exactly the kind of object that the models had suggested. The crust had broken somewhere, or the magnetosphere had twisted, and the result had propagated outward across 30,000 light years and arrived, in the pre-dawn dark, at the waiting instruments, a brief and ancient signal carrying one piece of a very old question home. What those instruments heard was not loud, and it was not long. It was a moment, but moments sometimes are enough. The galaxy that contains this magnetar, the one called SGR 1935 plus 2154, cataloged in the way astronomers catalog things, with a number that carries coordinates rather than a name, is a spiral galaxy, broad and slow-turning, roughly 100,000 light-years from one edge to the other. The Milky Way contains several 100 billion stars. Among those stars, somewhere between 30 and 35 magnetars have been identified, confirmed, or strongly suspected. They are not distributed evenly. They cluster. They gather near the inner disk, near the regions where star formation runs fastest and hottest, where the most massive stars are most likely to be born, near the dense molecular clouds that press together under gravity and collapse into new suns. Several of them lie within a few hundred light years of the galactic center itself, near the enormous black hole that anchors the core of the galaxy in its slow gravitational sovereignty. This clustering is not random. It tells something. Magnetars form from massive stars, stars considerably heavier than the sun, stars that exhaust their fuel quickly and die violently in core collapse events that send shock waves outward through the surrounding gas. The inner galaxy breeds those stars in greater numbers. The central molecular zone, the dense, turbulent region within a few hundred light years of the galactic center, is among the most productive stellar nurseries in the Milky Way, packed with molecular clouds warm enough and dense enough to collapse repeatedly into new generations of large, short-lived stars. The magnetars found near the galactic core may be telling us that this region produces precisely the kind of progenitor most likely to leave a magnetar behind. Massive, rapidly spinning at the moment of its death, seeding the next few seconds with enough turbulent energy to drive the dynamo that builds the field. It is not yet settled. The clustering near the center could reflect selection effects. We simply detect more of what is brightest and closest. The central molecular zone generates strong X-ray backgrounds that can obscure quieter sources. The sample is small. 30 sources across a galaxy of hundreds of billions of stars is a thin census, and the conclusions drawn from 30 data points carry wide uncertainty. What can be said is that the distribution of known magnetars traces the map of the galaxy's most vigorous star-forming regions, and that the inner disk holds the most of them, and that this is consistent with what the physics predicts. From that same inner galaxy, the light of SGR 1935 plus 2154 reached instruments on 4 continents. The CHIME telescope in British Columbia caught the radio burst. The Integral satellite caught the X-rays. So did Agile, and so did InSight HXMT. 4 instruments, different technologies, different orbits, different wavelengths, all reading the same event as it arrived. The coincidence, not a coincidence at all, but a confirmation, was precise enough to close a chapter and open a longer one. The longer chapter is this: if one magnetar in the Milky Way can produce a fast radio burst faint by extragalactic standards, then the far brighter bursts arriving from billions of light years away are consistent with magnetars at those distances releasing far more energy. The scale works. The physics is compatible. Not every fast radio burst need come from a magnetar. The universe is not so tidy, and there are other mechanisms that theorists have explored, but the April 2020 detection established beyond reasonable doubt that magnetars can make them, that at least some of what has been arriving, those millisecond flashes from the deep universe, originates in the same kind of object, a remnant stellar core, 20 kilometers wide, spinning slowly in the dark, its surface crackling with the slow violence of an extreme magnetic field. There are hundreds of fast radio bursts detected every year now, with newer, more sensitive instruments cataloging them across the sky. Some repeat, some appear only once, some show the periodic structure that might suggest a rotating source. A few cluster spatially, arriving from the same general region on the sky over time. The catalog grows, and within it, the magnetar explanation grows with it, not as the only answer, but as the one with the most evidence behind it, the one that connects most cleanly to known physics and known objects, the one that a single brief signal from a star in Aquila helped to anchor 30,000 light-years from where it began. What a fast radio burst carries is difficult to hold in ordinary terms. In a millisecond, a magnetar releases in radio waves alone more energy than the sun produces in days. Not in all wavelengths, in radio. The pulse is tight. It is narrow in time. It arrives as though something has plucked a string in the magnetic field, and the note has traveled outward at the speed of light, brief and sharp, and carrying within its dispersion the way different frequencies arrive at slightly different times after traveling through the thin electron gas of intergalactic space, a kind of record of all the material it passed through on the way. Astronomers read that dispersion like tree rings, inferring distance, inferring the density of matter between the source and the detector, building a picture of the intervening universe from the shape of the signal smear. The universe is full of this kind of indirect reading. Most of what is known about the cosmos has been inferred rather than visited. The temperature of a star's surface from the color of its light, the composition of a nebula from the bright lines its atoms emit, the distance to a galaxy from the speed at which it recedes, and now from the spread of a radio pulse across a millisecond of time, the density of electrons across hundreds of millions of light years of largely empty space. The magnetar, in this sense, is a kind of probe. It marks a position in the universe and sends out signals that can be used to map what lies between. Even its violence serves as a tool. There are other tools, other signals, other wavelengths in which the universe has not yet been heard clearly, but in which it is beginning to speak. Gravitational waves are distortions in space itself, the faint stretching and compressing of distance that propagate outward from objects whose mass is changing its configuration. Two black holes spiraling inward, two neutron stars colliding, a core collapsing at the center of a dying star. They travel at the speed of light. They pass through everything. They are extremely difficult to detect because the distortions they carry are vanishingly small, smaller than an atomic nucleus across a detector kilometers long. The first direct detection came in 2015 from two merging black holes, and since then, the catalog of detections has grown to include neutron star mergers, asymmetric supernovae, and a slowly filling library of collisions from across the observable universe. Magnetars have not yet been detected in gravitational waves. The instruments are not yet sensitive enough, but the physics suggests they could be. A magnetar with a sufficiently strong internal toroidal magnetic field, the kind wound in closed rings through the star's interior, never surfacing, possibly reaching strengths far beyond what the outer dipole field reveals, would deform slightly from a perfect sphere. The crust, held rigid by the strong magnetic stresses running through it, would bulge or indent in a way that depends on the geometry and the strength of what is buried inside. This deformation is called a mountain, not because it is large. It might be only a fraction of a centimeter in height across a 20-kilometer star, but because it is a departure from symmetry. And a rapidly rotating asymmetric mass radiates gravitational waves, continuously, at twice its rotation frequency. For a magnetar spinning once every few seconds, that continuous hum would fall in the frequency range of ground-based detectors. The signal would be weak, far weaker than any yet detected. But the coming generation of gravitational wave observatories, instruments planned and under development, larger and more sensitive than the current detectors, designed to push sensitivity down by an order of magnitude, may reach a threshold where the nearest, most active magnetars begin to appear, not as dramatic events, not as the single sharp chirp of a merger, but as a steady, quiet, persistent tone, a hum from a deformed star 20 kilometers wide, turning slowly in the dark, tens of thousands of light years away, its asymmetry broadcasting its shape in the language of bent space. The detection of that hum would be a different kind of knowledge. It would not be a burst or a flare or a pulse. It would be the magnetar in ordinary time, in its long quiescence between outbursts, its internal structure speaking through the only channel that passes without reflection or absorption through all the gas and dust and stellar bodies between the source and the detector. Gravitational waves see through everything. A magnetar detected in gravitational waves would be a magnetar whose interior has been heard directly, whose hidden toroidal field has left its mark on the geometry of space and carried that mark to Earth. That detection has not happened yet. It may happen in the coming decades. The instruments are being designed now. The sensitivity targets are being calculated now. Among the sources these future observatories might one day hear is a small rotating object in the inner disk of the Milky Way, its surface blazing in X-rays, its crust slowly stressed by the field that rests inside it, like a wound spring, turning and turning and turning in a darkness that has held it for thousands of years. There is another strand. It runs not from magnetars outward to the cosmos, but from the cosmos inward to matter itself, to the atoms of the heaviest elements, to the gold and platinum and uranium that appear in planetary crust and stellar spectrum and the cores of old stars, and to the question of where those atoms were made. The heaviest elements cannot be built in the ordinary nuclear burning of stars. Iron is the end of the road for stellar fusion. Below iron, fusion releases energy. At iron and above, fusion costs it. So the elements heavier than iron, the silver and barium and neodymium and lead and gold and beyond, require a different process, one that does not run on the gentle fusion chain of a main sequence star, but on a flood of free neutrons moving fast enough to build nuclei before they decay. This process is called the A process for rapid neutron capture, and it produces roughly half of all the elements heavier than iron in the universe. The sites where it runs must be extremely neutron rich, extremely energetic, and relatively brief in their duration. For decades, the candidates were narrowed by theory, without being confirmed by observation. Then came the gravitational wave detection of a neutron star merger in 2017, accompanied by a burst of light whose spectrum carried unmistakable signatures of freshly synthesized heavy elements. Kilonova light, glowing in the characteristic colors of lanthanide atoms newly assembled in the collision, drifting outward in the cloud of ejected neutron star matter. That detection confirmed that neutron star mergers are raw process sites, but the question of whether they are the only sites, or the dominant sites, or whether other environments also contribute, remains open. Among the other candidates are the first seconds after the birth of a magnetar, when the newly formed proto-neutron star is still hot enough and spinning fast enough to drive powerful winds of matter outward from its surface, carried by the enormous flux of neutrinos streaming from the cooling core. These neutrino-driven winds carry neutron-rich material into the surrounding supernova ejecta, and in some theoretical models, the conditions within those winds, the temperature, the density, the neutron fraction, are close enough to the R process requirements to synthesize heavy elements in the brief window before the wind cools and the neutron star settles into its long magnetic quietude. How much this contributes is not settled. The models differ. The observational constraints are difficult to apply because the heavy elements synthesized in a magnetar wind would be mixed into the supernova remnant and would look from the outside much like heavy elements from other sources. Disentangling the contributions of magnetar winds, neutron star mergers, and possibly other environments requires measuring the abundances of specific heavy elements in old stars that formed early in the galaxy's history, before many merger events had had time to occur, and comparing those measurements to model predictions that can isolate the different channels. The early universe made no heavy elements. The Big Bang produced hydrogen and helium and a trace of lithium. Everything heavier was built later, in stellar interiors and stellar depths. And the very heaviest, the gold in the ground, the uranium that heats the planet's interior, the platinum in laboratory instruments, were built in the most violent environments that stellar death produces. A neutron star merger is one such environment. A newly born magnetar, still hot and spinning, wreathed in neutrino-driven wind in the first seconds of its existence, may be another. Then atoms that emerged from those events drifted outward, and mixed and cooled and condensed and drifted again across billions of years, until some of them arrived, by accident of chemistry and gravity, in the places where they now reside. The gold that occurs in the ground is not a familiar thing. It is old. It is made in the hottest, densest, briefest events the universe produces. And some of it may have been assembled in the wind of a newly born magnetar in the first 30 seconds of that object's existence, before the dynamo stopped and the field locked in place and the long, slow life of the magnetar began. This is not established. It is a hypothesis, held carefully, tested against data that can only constrain it rather than confirm it. But the hypothesis is serious, and the evidence does not rule it out, and the search for our process sites continues in the spectroscopy of old stars and in the future gravitational wave detections of neutron star mergers, and in the models of early cosmic chemical evolution. Magnetars are part of that search, not as the certain answer, but as one candidate in a question that belongs to the history of every heavy atom in the solar system. The magnetars that can be named and studied are all within the Milky Way, or within its satellite galaxies, just beyond. The nearest well-studied ones are several thousand light-years away. At those distances, even the most powerful outbursts arrive as detectable signals, rather than dangers, the radiation diluted by distance to levels that instruments can measure, but that pose no threat to anything on the surface of a planet, orbiting a quiet star, several thousand light-years away. The most energetic outburst ever detected from a magnetar, the giant flare of December 2004, released more energy in its first fraction of a second than the Sun produces in 250,000 years. It traveled from its source and arrived at Earth as a measurable brightening of the ionosphere, a faint disturbance in the electrically charged upper atmosphere, not a danger, a signal. But the December 2004 flare was also detected from galaxies beyond the Milky Way, and that fact points somewhere interesting. The source, SGR 1806-20, is thousands of light-years away within the Milky Way. The flare was bright enough to affect Earth's upper atmosphere at that distance, and from other galaxies, at distances measured not in thousands but in millions of light-years, astronomers have found events in the gamma-ray record that look like exactly what such a flare would look like from far away. Brief, with the right spectral character, too soft and too fast, and too energetically consistent with a magnetar giant flare to be comfortably explained as collisions of compact objects at cosmological distances. One of these extragalactic candidates was associated with the galaxy M81, a spiral galaxy roughly 11 million light-years from the Milky Way, a galaxy visible on a clear night through a small telescope as a faint smear of light in the northern sky. Its hundreds of billions of stars unresolved into the tidy spiral that long exposure images reveal. An event recorded in the early 2000s, known as GRB 051103, has been matched to that galaxy in position and characterized in duration and spectrum, and the match is consistent with a magnetar giant flare from within M81 rather than a cosmological gamma-ray burst from somewhere much farther behind it. A second candidate, GRB 200415A, was localized to the galaxy NGC 253, also called the Sculptor Galaxy, roughly 11.5 million light-years away, a bright and dusty edge on spiral in the southern sky. Its detection was brief, a few tenths of a second of intense gamma radiation, and its properties, when examined carefully, match the physics of a magnetar giant flare more closely than they match the physics of a short gamma-ray burst from a neutron star merger. The localization was tight enough to exclude most of the sky and point to that galaxy with confidence. These extragalactic detections matter for a reason that goes beyond the science of magnetars alone. They establish that the most extreme magnetar outbursts are visible, with current instruments at distances of 10 to 15 million light-years. That is a volume of space containing dozens of galaxies. The next generation of gamma ray observatories, with greater sensitivity and better localization, will push that horizon outward, perhaps to 50 million light years, perhaps further. In that expanded volume, thousands of galaxies lie, each containing its own population of active magnetars, each capable of producing events that could be detected and identified and added to the catalog. The extragalactic magnetar flare catalog, which currently holds 2 candidates and a handful of less certain events, will grow. The statistics will improve. The rate of such flares per galaxy per year will be measurable, and from that rate, something can be learned about the birth rate of magnetars, the fraction of massive stars that produce them, the distribution of field strengths across the population, and the depth of the physics that drives the most extreme magnetic fields in the universe. The universe is built of layers, not layers in space, though it has those too, but layers of accessibility. Some things are close and bright and easily measured. Some are far and faint and require instruments that do not yet exist. The magnetar story occupies all of these layers at once. Within the Milky Way, it is a story of individual objects with names and coordinates, with measured spin rates and surface temperatures, with historical records of outbursts and quiescent intervals. Across the local galaxy group and the nearer clusters, it is a story of events, brief flares that arrive from distances of millions of light years, identified by their character rather than their source. And at cosmic distances, it is a story of populations, of what fast radio bursts and their dispersion measures can tell about the density of the universe they traveled through, of what the rate and brightness distribution of events says about the magnetar population as a whole. Each layer uses different instruments, each layer asks different questions, and the answers from each layer do not stay in their layer, they travel between. What is learned about the internal structure of magnetars from the seismology of their crust, from the quasi-periodic oscillations that ring through the star after a giant flare like vibrations in a struck bell made of nuclear matter, constrains what the models say about the maximum brightness of a giant flare, which constrains the detection horizon for extragalactic events, which constrains the rate estimates, which constrains the birth rate of magnetars, which constrains the models of what massive stars become when they die. Everything connects. The vibrations of a 20-kilometer object in the inner Milky Way echo through the equations that describe galaxies millions of light years away. The atoms synthesized in a magnetar's first 30 seconds of life are potentially readable in the spectra of old stars in the Milky Way's halo. The dispersion of a millisecond radio pulse carries the fingerprint of the intergalactic medium across billions of light years. The magnetar is small, but the threads that run from it do not remain small. They widen outward through astrophysics, through nuclear physics, through the large-scale structure of the cosmos, until the question of what a magnetar is and what it does has become the question of where the heavy elements come from, and what makes a fast radio burst, and how the universe distributes its most violent magnetic energy across space and time. There are 30 of these objects that are known. 30 in a galaxy of several hundred billion stars. If each were a grain of salt, the entire population would fit in the palm of a hand, grains too small to feel individually, but collectively visible as a white dust. They are by the numbers almost nothing, a fraction of the galaxy's stellar census, brief in their active phase, 10,000 years of intense magnetic violence before the field begins its long decay and the magnetar quiets into something slower and less extreme. Against the age of the galaxy, 10,000 years is almost nothing, a blink spread thin, And yet those 10,000 years contain the most energetic non-nuclear events that can originate from a stellar remnant. The flares, the bursts, the quasi-periodic oscillations of the cooling crust, the continuous X-ray glow that outshines the sun by factors of 10,000 or more, even in quiet periods, the distortion of local spacetime by a magnetic field so strong it warps the geometry of atoms, all of it concentrated into those 10,000 years, and then gone, the field fading, the star cooling toward the long quiet of an ordinary neutron star. 10,000 years. In cosmic time, it is a moment. In that moment, more happens per unit mass than in almost any other configuration of matter in the universe, and then the moment passes, the field weakens, the outbursts grow less frequent, the X-ray luminosity falls, the spinning remnant slows and cools and fades toward the background. What was extreme becomes ordinary. Over time, what was volatile becomes stable. The most violent magnetic objects in the known universe age, like everything ages, and settle into something quieter and continue. Somewhere in the Milky Way, at this moment, a magnetar that formed 1,000 years ago is still in the full intensity of its active phase. Its crust under magnetic stress, its surface blazing in X-rays that no eye will ever see directly, its field driving slow currents through the nuclear matter of its interior. Somewhere, a magnetar that formed 9,000 years ago is winding down, its outbursts becoming less frequent, its field decaying on timescales that will eventually carry it across the threshold into something no longer magnetic enough to distinguish from the quieter neutron star population. And somewhere, the remnant of a magnetar formed 30,000 years ago has already crossed that threshold, its field weakened, its surface cooled, turning slowly in the dark with no marking that distinguishes it from the hundreds of millions of ordinary neutron stars that share its galaxy. Each of these is the same object at different points in a long life. Each is the same physics expressed at different intensities. The extreme does not last. It never lasts. But while it lasts, it shapes the material around it, the hot gas expanding outward from the supernova that made it, the chemistry of the ejecta, the ionization of the surrounding interstellar medium, the heavy elements drifting outward in the neutrino wind, the fast radio bursts traveling for thousands or millions of years to arrive at instruments that were not yet built when the pulses departed. The effects of what a magnetar is and does persist long after the active phase ends, woven into the chemical and structural record of the galaxy, in ways that outlast the magnetar's own intensity by billions of years. The gold atom is patient. It formed in a flood of neutrons, perhaps in the wind of a magnetar in its first seconds, perhaps in the fire of a merger between two neutron stars, and it drifted and mixed and cooled and condensed into rock and crust and ore, and it will persist through the death of the star it circles, if a star it circles, and through whatever comes after that, for longer than stars will burn. The magnetar that may have made it is long gone into quiet. The atoms remain. The radio pulse called FRB 200428 arrived at Earth in April 2020, traveled across 30,000 light years to reach the instruments that recorded it, and was gone in less than a second. The conversation it completed had been building for years. The question it answered had been asked since the first fast radio burst was found in archival data in 2007, and the source that sent it is still there, still turning, still bright in X-rays, still cataloged and watched by telescopes that scan the inner galaxy for the next outburst, the next pulse, the next piece of information carried outward at the speed of light from something 20 kilometers wide and older than recorded human history and stranger than almost anything the universe contains. The gravitational wave observatories are waiting. The next generation gamma ray telescopes are being planned. The spectroscopic surveys of old halo stars continue their patient work. The catalog of fast radio bursts grows entry by entry, burst by burst, each one carrying the dispersion record of the matter it crossed and the timing precision of an event that lasted less than a heartbeat. And in the quiet intervals between all of this, in the hours when no burst is arriving and no flare is brightening any detector, the magnetars turn in the dark of the inner galaxy, slowly as they have turned for thousands of years. They are not aware of being watched. They have no awareness of anything. They are matter, dense and extreme and magnetic, doing what matter does under extreme conditions, converting field energy into heat and light and occasional violence, decaying slowly toward equilibrium, persisting in the interim as one of the most extraordinary configurations that physics allows. The watching is entirely on one side. The instruments, the models, the patient accumulation of data across decades, all of it is the work of a species that has been looking at the sky for only a brief moment of the galaxy's long life, trying to understand what it contains. What it contains, among other things, is 30 grains of salt spread across 100,000 light years, each one blazing in X-rays, each one the remnant of a massive star that died billions of years before the Earth existed, each one briefly, intensely, incomparably magnetic, and then slowly, inevitably, less so.